All right, let's look at four basic examples applying the fundamental theorem. And in each one of the cases except the first one, we'll have to make minor adjustments, right? The thing is not, all of these are not set up and ready to use the fundamental theorem right away. So here are the four examples we want to look at. They're all accumulation functions, and we want to find the derivative in each case. So essentially, we want to cancel out the integral sign in each case with a small adjustment. So the first one, it's the integral from 3 to x of 1 over 1 plus t squared dt. The second one goes from x to pi, square root 1 plus secant of t dt. The third one goes from 0 to tangent of x. So now instead of just an x in the upper limit, we've got a function of x in the upper limit. Square root of the quantity alpha plus square root alpha d alpha. And then in the fourth one, now we've got both limits of integration are functions. So the integral from 2x to 3x, u squared minus 1 over u squared plus 1 du. So in each case, we want to find the derivative. In each case, except the first, we'll have to make a small adjustment. Okay, the first one's really easy. We've got a continuous function, 1 plus 1 over t squared, and the integral goes from some constant a to the variable x, and we want to find f prime of x. So the fundamental theorem says if I want to take the derivative of this thing, so d over dx, 3 to x, 1 over 1 plus t squared dt, right? These two operations will cancel. I just replaced t by x, and so 1 over 1 plus x squared would be a good final answer, right? So when I differentiate the integral, that's going to get rid of the integral, replace t by x, and then we're done. Okay, remember the fundamental theorem says if we want to differentiate the integral from a to x, then all we need to do is remove the integral sign and replace t by x. But that form says that the lower limit needs to be a constant and the upper limit needs to be variable. So here we've got the lower limit is the variable and the upper limit is the constant. So let me call this capital F. Right, so now this tells me that capital F of x is the same thing as negative the integral from pi to x, square root 1 plus secant of t dt. And so the derivative then is just going to be, now we can replace t by x. So this says that f prime is negative square root 1 plus secant of x, and then that would be a good final answer, right? Okay, here we want to make use of the chain rule. So now we've got our upper limit is a function of x. It's not just x. So here's what I'm going to do. Let me let u equal tangent of x. So let me let u be the upper limit, and let me call the function capital F of x, let me just call that y. So we know that f prime of x is the same thing as dy dx. But we know that dy dx is the same thing as dy du times du dx. Okay, so if I rewrite this thing, we know that y is equal to the integral from 0 to u square root alpha plus square root alpha d alpha. So now, what is dy du? So the derivative of the integral with respect to u. Before, if there was an x here and the derivative was with respect to x, I just cancel the integral sign. Now it goes from 0 to u, and I want the derivative of y with respect to u, so I just replace all the alphas with a u. So now this thing is the same thing as square root u plus square root u, right? That's this part. And then times du dx. So we're almost done. Now we just need to fill in everything with what u really is and what du dx is. And so in this case, let's say f prime. So now f prime of x is going to be square root tangent of x plus square root tangent of x. And then we want to tack on the derivative du dx. Well, remember, u was tangent of x, and so du dx is just secant squared of x. So this would be a good final answer for this problem. Again, what did we do? We replaced all of the alphas with the upper limit, so I got square root tangent of x plus square root tangent of x, and then just tack on the derivative of the upper limit. So just remember to do that whenever you've got an upper limit of integration that's a function of x and not just x. All right, here we've got both limits of integration are functions of x, not just an x. So here's the line 2x and here's the line 3x. So these functions are different. And so I can insert in here some constant, call it c. So here's the lower limit of integration, and then the upper limit of integration is going to be directly above. So let's just insert some constant c. It doesn't matter what it is. So this is the same thing as the integral from 2x to c, u squared plus 1 over u squared minus 1 du, plus the integral from c to 3x, u squared plus 1 over u squared minus 1 du. So remember, when you've got the integral from a to b, that's the same thing as the integral from a to c plus the integral from c to b. Okay, so this thing we can apply the fundamental theorem because it goes from a constant to a variable upper limit. Here, it goes from a variable lower limit to a constant. So in order to apply the fundamental theorem, we need to switch the limits of integration. So this is negative. The integral from c to 2x, u squared plus 1 over u squared minus 1 du. And then here we've got the integral from c to 3x, u squared plus 1 over u squared minus 1 du. So this last one didn't change. So now what's f prime going to be? So f prime of x, right? I'm going to replace u with 2x and then tack on the derivative of 2x. So I get negative. All right, so f prime is negative 2 times 2x squared plus 1 over 2x squared minus 1. So there's the first piece. And then the second piece, I'll replace all the u's with 3x and then tack on the derivative of 3x, which is just 3. So plus 3 times 3x squared plus 1 over 3x squared minus 1. And so this would be a good final answer for the derivative